Okay, this video is going to be a very gentle introduction to Matlab and Octave. So I'm going to be working in Octave in the video, but everything that I do in Octave will be also essentially equivalent to what you would do in Matlab. So they're more or less interchangeable for the type of work that I'm going to do here. Um, we're going to be doing a very simple circuit analysis of this DC circuit here. So before I actually jump into Octave to do it there, we're just going to run the simulation in LTspice just to see what the circuit does. So it comprises a 10 volt DC source. So I've used the generic voltage source in LTspice, but I have configured it as a DC source. So you can see I've just filled in a 10 volt DC value there. And I've got these two resistors in series, R1 and R2. R1 is 30 ohms, R2 is 20 ohms. So there isn't much to this. Let's try running the simulation and see what it does. Now I'm using the transient analysis here. I could probably use one of these other DC options, but I'm just going to run it for a couple of seconds and we should just get constant values out here. So let's look at the node voltage at the upper node here. I'll just maximize this here so we can see it more clearly. Let's tile those windows. So if we look at the upper node here, this should be the supply voltage, so that should be constant at 10 volts, and you can see that is indeed constant. And if I look at the voltage in between the two resistors, so this is basically just the voltage across R1, that should be 6 volts, I think, and yes it is. So if I adjust the scale here, just to bring the bottom down to 0 volts, we'll be able to get a clearer picture of that. So we've got the voltage across R1 is shown in blue there, that's 6 volts, and then the full supply voltage is 10 volts. So those are basically the results that we're expecting to get when we do the same analysis in Octave in a minute. Just one more thing that I should measure while I'm here is the current passing through the two resistors. So because they're in series, the same current passes through both of them. So it doesn't really matter which one I click on. I'm clicking on R1 there, and you can see that it is measuring the current through R1, which is a constant 200 milliamps. So assuming we get the same values in Octave, then we'll know we're basically doing things correctly, right? So let's maximize this in case we need to refer back to it. And I'll switch over to Octave. So in Matlab and Octave, what you'll be presented with first when you open it up is a command line waiting for you to type in commands here. And in the very simplest case, you can just use Matlab or Octave as a kind of a desktop calculator. So you can do simple calculations just by typing in mathematical expressions. They'll be calculated on the spot. It'll have certain mathematical constants built in, like pi. Mathematical functions like sine. Let's just put in sine of pi over 2. So that's sine of 90, which should be 1. So you can use it just the same way as you'd use a calculator, just by typing in mathematical expressions. Expressions, and in fact it's very useful using it. Excuse me. It's very useful using it in that way. However, if we want to type in a longer sequence of commands, we would normally store them in what we call an M file. So it's a type of a script file. And there's an editor built into both Matlab and Octave for typing in these M files. All an M file is it's just a list of the commands that we could type in at the command prompt here. But by storing them in a file, we can create a long sequence of them that we can repeat just by rerunning the same file. So for doing a circuit analysis, if it's a very simple circuit, I might just type in the steps here at the command line, but more likely I will write the steps into a file in case I want to rerun the calculation or modify the parameters or whatever. So I'm going to click on New Script up here in the toolbar, and that will open up the editor, and I'm going to type in a sequence of commands here that will be executed in order when I run this M file. So I'm going to create a few variables to store some of the information from our circuit. So in particular, we're going to have a variable for the supply voltage, which in this circuit here is shown as V1. And that's just equal to 10 volts. So I'm just going to say V1 equals 10. Now you can either put on a semicolon or leave it off on the end of a line. The difference is when you run a command with a semicolon on the end, so if I said V1 equals 10 with a semicolon, it doesn't print anything out. But if I run the same command without the semicolon, it just answers back to confirm what operation was carried out. So it'll like echo the same thing that you've typed there will be printed out. Now when you're running a longer script, you often don't want to see everything getting printed out. So to make a lot of the lines run silently, you just add on a semicolon on the end. So when you see a semicolon on the end of a line, the purpose of it really is not to actually change what the calculation it's not to change the values in the calculation or anything like that. It's just to limit the amount of text that gets printed out on the screen, so it's not just scrolling unnecessarily. So in this case I'm going to say V1 equals 10 and I'm going to put on a semicolon there. We've got a couple of resistances here, so I've got R1 which was equal to 30 ohms. So to say R1 equals 30, and I have R2 equal to 20 ohms. So what can I calculate here? Well, there's a couple of different ways that you could do this calculation. I think what I'm going to do is I'm going to calculate the overall resistance of R1 in series with R2. So I'm going to say R is equal to R1 plus R2. So this is the total equivalent resistance of the two resistors in series. And then once I know that, I can calculate the current in the circuit just using Ohm's law. So V is equal to IR, or equivalently I is equal to V over R. So in this case the voltage is the voltage coming from our 10 volt DC supply, and I'm going to divide that by the total resistance in the circuit, which is R. That's the sum of R1 and R2. In this case I'm going to leave the semicolon off because I actually want to see it print out what the value of I is. So that's my M file. I haven't saved it yet, so before we run it, let's save that file as, what will I call this? Let's just call it DC circuit. The .m file extension will be added on automatically, I think, on the end there. And the directory that's currently saving in for me is home user. That will appear slightly differently in Matlab, but there will still be an address bar somewhere up the top here indicating the current directory where your file is being saved. And you can see there's my file name. So I'm actually not sure, looking at that, whether it saved it with the .m extension. I guess we'll find that out in a minute. So down at the bottom of the screen here, I'm switching between the editor and the command window. So the command window is where you type in commands and they're executed immediately. The editor is where you're actually typing them into a file and then you're going to store the file. But whatever sequence of commands we've stored here, we're going to run that in the command window, and then it's going to carry out all those commands in sequence. So I'm going to type in DC circuit. Yeah, actually it didn't store the .m, so I'm going to resave that file just for technical correctness here. I'm going to save as, no, sorry, not there, file, save file as, and this time I'm going to save it as DC circuit.m, which is the correct file name extension. You can see once it's stored as a .m file, it color codes some of the syntax because it recognizes that it should be a sequence of Matlab commands, and it'll recognize certain things like the operators and the semicolons and so on here. So once I have that saved, I can switch to my command window and run that file. So DC circuit.m. Actually, yeah, better just delete that other. So now I can just run DC circuit and you can see it calculated, well, it's carried out all the steps, but the only one that's produced any output is the very final step, which was calculating I, and indeed it has printed out 200 milliamps, so 0.2 of an amp. If we compare that to what we got in LTspice when we simulated, we got exactly the same answer, 200 milliamps. So that looks pretty okay. Now one thing I'm interested in calculating is what is the voltage across OR1. So if we look back at that circuit there, you can see we've got 200 milliamps flowing down through these two resistors. So we can use Ohm's law to calculate the voltage drop across either one of these resistors. We know that the two voltages have to add up to 10, but the question is how many volts are dropped across each of these, right? So it's going to depend on their individual resistances. And now that we know the current passing through them, we can use Ohm's law to calculate the voltage between their terminals. So I'm going to do that for OR1. Where am I going? Here we go. So back to my editor in Octave or Matlab, and I'm going to edit this M file again. So we got as far as I is equal to V1 divided by OR, but now I'm going to say the voltage on OR1, which I'm just going to call VOR1, is equal to, so V is equal to IOR, that's Ohm's law. So in this case, I is the current in the circuit multiplied by OR1, which is the resistor that we're interested in calculating the voltage across. I suppose we might as well calculate the voltage across OR2 as well while we're doing this. So it's a V OR2 is equal to I times OR2. The exact same current passes through both resistors, so you can apply Ohm's law to each of them. It's the same value of I, but different resistance in each case. I've chosen to leave off the semicolons here again, just so we can actually see those answers getting printed out. So in this case, we're going to see all three of these lines produce some output on the screen when we run this. So I'll just run DC circuit again. Oh, sorry, I haven't saved those changes. So I need to go back and save it. And this time when we run it, we should see those additional lines of output appearing. So you can see the current was calculated again as 0.2 amps, that's 200 milliamps. VOR1 is 6 volts, VOR2 is 4 volts. So that in a nutshell is how we would do like a very simple circuit analysis in Octave. In the next video, I'm going to build on this to introduce complex numbers. So really one of the main reasons that we would actually use Matlab or Octave for doing this type of calculation is when we're doing phasor analysis, we're going to need to use a lot of complex arithmetic. So adding, subtracting, multiplying and dividing complex numbers. And Matlab and Octave are going to make it very straightforward to do that. So we'll be able to do an analysis similar to what we've done here, but with complex numbers which will represent sinusoidal voltages and currents. But I'll end this video here though.